So let's get started. So today's session, we'll talk about robotic software development in general. It's kind of like a two-part series. I was actually giving a lecture at Carnegie Mellon for one of the courses, and so I gave two lectures, and I just wanted to present it here for people who are interested in listening to that. So this is kind of like a general uh, lecture on robot software development, and robot ROS is kind of a major part of it. So that's why we are focusing on ROS. Um, Eventually, we'll also look at some how to do this thing with AI tools. I don't know how far we can get through, like if we can complete this whole lecture today. So I'll try to push through it. If not, we can pick up next week from where I left off and then go from there. Okay. And throughout this thing, just stop me at any point. It's not a formal thing. Just stop me at any time, ask questions, and that is the best way you can learn. If you're just listening through as like a YouTube video, that's not going to help. So just stop me at any point and ask questions.
Got it.
Okay.
Okay.
Cool. So let's get started. So the first thing about ROS, right? So this is what the ROS, like if you go to the ROS website, this is what it says. So it is um, it's an operating system with a set of libraries and tools that help you to build robot application. So one thing that we have to make clear is like when you say operating system, depending on what connotation you use, you might think of it as like, oh, it runs on the bare metal, like on the hardware, but it's not an operating system in that sense. It is more like a middleware that takes care of talking between different components in your software setup. So this forms a layer on top of your operating system, not like running bare metal. And basically, it's a set of libraries and tools. We'll go in detail on what that means. And then one of the major things about ROS is like it says from drivers to state-of-the-art algorithms with powerful developer tools. So these are all like the most important things about ROS that made it really famous and useful. So we'll talk about each of them, like the state-of-the-art algorithms, the powerful developer tools, and why those are important. And another thing that made it all the more powerful and useful is it was open source, right? So it is a pretty liberal kind of usage thing. So any company can also get and use ROS without having to pay a royalty. So that's another reason why ROS became really famous. So that's kind of like the first bit about ROS. So um, before getting into the details or before talking about ROS much in detail, I wanted to give you some context on why ROS became famous and what is the what's basically set the context for that. So before ROS or any such systems were prevalent, the most common way for um, components or like software components to talk to was using the client server architecture. What I mean by that is you have some kind of a server, some kind of a client. The client should know who the server is or who it's talking to. The server needs to know who the client is and who it's talking to. And when you want to bring up the system, you bring up the whole thing. If one is absent, your system will not come up and all those things. So that's kind of like the traditional way of setting up software. And then this idea about this message passing architecture came into play. So this is more like it's a little different from the client-server architecture where you have a common message bus, and there is no notion of server or client, and each one just sends it to this common message bus. So when I say common message bus, we are basically getting rid of this central dependency where like you have one component and if that goes down, everything goes down along with that. In addition to that, there is also this additional thing where if you don't need to know who you're talking to or who's listening to you, which when you get rid of that dependency, what that really means is you don't have to worry about is the listener running or is the sender running. And so you can have systems that are coming that can come up like um, separately and still have the whole thing set up or testing and things like that. So it'll become a little bit more relevant as I go through, but um, this is kind of the major change in architecture that kind of like made it really famous and useful compared to the previous kind of frameworks. So I just wanted to show how this works. So this slide I wanted to show an example of how a client-server architecture would apply for a typical robotic system. So let's say you have a system where you have a camera and an IMU, and you have some kind of a stereo processing for a camera and a mapper and a position estimator that is taking so the mapper would take data from your stereo and the IMU, build a map. The position estimator would take the IMU and build the map and sorry, it will generate the position and then give it to the mapper. So the mapper basically needs data from the IMU, the position estimator, and the stereo processor. And the planner takes in the map and the position estimator and plans on top of that. Kind of a typical system how you would do setup. In a closely, I mean, so in a client server architecture, what really happens is you have this tight coupling. What I mean by that is each component would need to know who is talking, who it is talking to, and if that component is not coming up, then the other component would not even work. So in this case, the planner, if the mapper is not coming up, then the planner wouldn't probably come up. So you have to like have these components running, and also you're kind of expecting the mapper to send the data. So let's say you've developed a different version of the mapper and you want to test with the system, you cannot have both the mapper coming up together because that would conflict and the planner will not know who to talk to. That's kind of like how a typical traditional system with a client-server architecture would work. Whereas in a message passing system, it'll be different. So each component will be run separately, and each of them would publish to a common message bus. And whoever is listening to the data would pull data from the common message bus. So in this case, each of them are loosely coupled. So you can just run the IME driver fine or the camera driver without having to worry about who's listening to those data. And you can still come up, like run the position estimator without knowing if the IME driver is still up or the mapper is up to listen to the data. So that kind of loose coupling, it looks like, okay, this is obvious. Like, why are we even talking about it? But this was a major thing. Like 20 years ago, this was not the architecture. It was like the client-server architecture. And if you programmed things then, you would have realized that it's really painful to have some systems like that. I mean, there were still systems that were built that way, but they were really hard to scale. That's where this whole thing comes in, right? So now we have ROS software that has like hundreds of nodes, basically hundreds of these different entities that are talking together. If you want to set up a system using these client-server architecture with these hundreds of nodes, it's a total nightmare. It won't be like easy to debug them at all. And that was kind of a major big change or need that kind of like ROS satisfied. So that's the kind of the high level bit on the architecture. Let me stop here briefly and ask if there are any questions. If you kind of get this idea, then you know like why we're using ROS, right? Like what's going on. Any questions?
Not at the moment.
Okay. Cool.
No, nothing from my side.
Okay, sounds good. So let me keep pushing through. So the next part is as I said, with this message passing system, you can think of things as the components, right? So this is basically a component-based framework. So you have once you're in the component based development, you can just develop individual components separately, right? So if you want to develop a driver for your node, for your hardware, you can just start writing the driver for that. So you could have like separate programs or nodes that are designed for each component. Also, you can package algorithms into these component setups. So you can have separate components for each of these different algorithms. And that applies to not just like simple object detection and things like that. It can also have like major algorithms that depends on other algorithms. Like for example, navigation might depend on a couple of other nodes that form together to kind of help with the navigation. So you can have this orchestration of multiple nodes, and that's what this kind of setup allows. So what is ROS in general, right? So talking about it, I mean, I initially mentioned that it's a robot operating system, but I did say that it's not an operating system in the traditional sense. So what essentially is it, right? So it is a couple of things. So ROS basically provides infrastructure, tools, capabilities, and community. So it's a combination of these four things that makes the ROS that makes up or builds ROS. So let's look into each of them separately, like what each of them actually provide. So when I say infrastructure, I'm basically talking about the middleware architecture. So I said that we can have different components, right? So for having this different components, you need to have this middleware layer that lets these components to be talking to each other, to be configured and used, right? So an operating system itself would just let you create processes. These nodes are running as processes, but just processes is not sufficient. You need to have some mechanisms for them to talk to each other, some mechanisms to say that, okay, this is what forms the node, and basically configure the node, saying that how fast they can publish, or and what kind of queue they can have on the subscriber, things like that. So in addition to that, so it provides these client APIs for communicating between nodes over the network. So ROS is primarily talking through the network. That's kind of like an interesting design decision that they took. It has both positives and negatives, but the positives kind of outweigh the negative. So in a typical traditional old way of set up things, you would basically use inter-process communication to talk between nodes when they're running on the same computer. You wouldn't rely on network-based communication. The upside is basically it makes things faster, but the downside is it makes it really tightly coupled. Whereas ROS allows you to do things on the network interface. Basically, what that means is even on the same, even if the processes are running on the same computer, you would use the network interface to talk to stuff. It's not super inefficient, but it is a little, if a little kind of inefficient than interprocess communication. But the upsides are it lets you run the nodes on a different computer now because it's using the internet network interface. So the other part of it is with all these development and um, efficiencies in computing, this is no longer a big deal, right? Like we are not like pressed for computing as we used to like 20 years ago. So the downside is actually not that much of a big downside. If you're thinking about like micro or like even yeah, if you worry about like microseconds, which is like thousands of a millisecond, then yeah, sure, networking, there is going to be a hit compared to shared memory based kind of operations. But most of the nodes and ROS are probably don't care about those kind of information, those kind of delays. So that is why it is better kind of a design choice that ROS took that kind of helps in this. Um, so then there are also these tools and file formats for assembling the nodes into system. So essentially, you can think of ROS as a way to architect your system. It helps things in system engineering. So you can now think of things as components and blocks, and you can use that to assemble a system like a Lego system. Um, And then the next part is like it provides a package system for building and sharing components. So what that means is in the past, if you're building or if you're using some algorithms or some data that someone else has, well, not the data, but if you have some algorithm that you want to use, you would look for their code somewhere, and you'll have to package it in a way that works with your system. And then that by itself takes a lot of effort. In ROS, you basically it says like how a node should be defined. Like there are rules on how you set up a system and how it should be packaged. So you can just get it off the internet and just get these things working up and running in a couple of minutes compared to like hours or even days that it used to take. So if I mean these are things that that might look obvious and kind of alienated to you guys. Like if you're not used to developing things for the past 20 years, this might be like, oh yeah, this is all obvious. Like why are we even talking about it? But um, 20 years ago, this was not the common use case. People used to spend a lot of time. I used to spend a lot of time building, getting things, setting it up, and making things work in the field. So one of the last thing is also the build system. So you guys have used ROS to some extent, and you know that it uses CMake and then the Catkin system on top of that. But like 10 years ago, primarily when I was joining CMU, uh, when we get used to get some algorithms, it could have different build system. It could have make or CMake or something else, and when just trying to integrate that into our build system would be really painful. It is not trivial. It was not transparent. Sometimes we spent like days to even get that system to build along with our system. So ROS kind of like normalized and standardized those things. So now you can just get it and just build it and it just works fine. So these are things we take it for granted, but these are the developments that really helped robotic software progress. On the tool side, this is another big thing that Ross brought to the game, which is having tools to introspect and see what is going on in the system. So it might seem like, yeah, sure, tools. So what's so important about it? But when you actually start developing, you'll be like, oh, I'm running this node. I don't know what is going on. Is this node really up? Is this is it sending the messages that it should send? Is this guy listening to this message? At what rate is it sending? These are things that comes up. And if you have like a closely coupled or client server based architecture, there is no way of you knowing that. You have to like either have this introspection in your node itself so that it every time it prints that it send the message or it's sending at this hugs. So that's a lot of code that is being like rewritten. Or you don't have any kind of like transparency at all, and you just hope that things would work. With ROS, you just write a node, but you don't have to know whether you don't have to write any code that says whether this node is running, whether that node is sending something, at what rate it's sending, and which other nodes are listening to it. So these kind of tools is what Ross developed early on, even before the framework became well established. And that is one of the reasons why Ross became really famous compared to other frameworks that were around that time. So that tools is a big deal on that front. So Ross also has, I mean, so I've listed some tools here like the RQT, Ross CLI, and Ross Bag. So these are the tools that basically helps you to kind of like look at what's going on. Ross Bag is another big thing where it lets you collect data and play it back as though the sensors are all running in real time. So this is one thing that helps a lot with um, developing things like for simulation, because not like when you're developing some robotic projects, you would not have access to the robot all the time. The robot access is going to be pretty limited, so you would be developing stuff in the simulation a lot of times. And if you have something that can play back things at the exact same in the exact same way as how it is done when you're collecting the data, then it becomes a lot more useful. In the past, when you have to do this, you have to develop everything, like you have to write the program that does this collection and also play back at the exact same time. And it has different issues like bottlenecks and things like that. ROS kind of standardized that. And um, so one of the important feature in ROS, I would say, is like ROS bags. And people like almost all the people who use ROS bags. And then comes the capability. So this is like the more technical part of things where ROS kind of shines. So these things came after the infrastructure and the tools were set up, that this had like a really good kind of ecosystem. Now people started putting in a lot of different algorithms and state-of-the-art uh, programs into the ROS framework, because it's all like portable and easy to pull in and run. So it has algorithms for perception, planning, localization, mapping, state estimation. So anything that you can think of, it's probably in some ROS repository, and you can pull up and use it. Drivers is one major thing. Again, so you get uh, hardware, and then you want to integrate that into your software stack. In the past, you have to run it, and you have to go and look for their API, the from the hardware manufacturer. Most of the time, it's kind of crappy, and you get that API and you try to integrate that into your system. Sometimes the APIs are written in Visual Basic or something like that. And then what that means is you need to have a Windows system to run it, and not you cannot do it on a Linux-based system. And that would be a major blowback, because then you need to figure out how you can communicate. And I've spent hours, days, and even months trying to get a hardware into a robotic software package, or like a software stack. With ROS, I think people started developing these drivers and releasing it as ROS nodes. So any famous hardware that you get, you just look up, and there'll be some kind of ROS um, driver for that, and you can just get that and run off the shelf. So that kind of pushes your development time, like reduces your development time a lot. So that's another major kind of important capability. So with all these came the community, right? So with great infrastructure tools and a lot of capabilities, the community came together. And for any framework to be used and to become famous, there has to be a vibrant community behind it. So Ross has this vibrant community, and they also have these different ways in which the community can interact. So they have these community events like RossCon, and these are conferences that you can attend, where they kind of like discuss on where Ross is, how you can take Ross further, and things like that. And there are also these working groups that kind of look at Ross and how to specialize Ross to specific areas, like space Ross, where they're trying to specialize ROS so that you can use for space applications. And industrial ROS is something that where they look at ways to use ROS in industry, where you need more reliability than all the cutting edge kind of features. So these are the things that brought ROS together, and and makes ROS what it is right now. Okay, so I'll take a brief pass here, and I'll ask if there are any questions.
Yeah, at the moment, nothing from my end. No,
Okay,
yeah.
cool. Let me see if I have.
Nothing from my end, Chris.
Okay, cool. Okay,
All
so
set.
okay, sounds good. So let's keep pushing forward. So so ROS is basically called sometimes the Linux of robotics, right? So Linux is one like an operating system that came up with kind of made a lot of software flourish. with the open source kind of setup. And ROS is compared to the Linux of robotics because once ROS came into picture, this huge flux of companies and research and um, research labs that kind of started contributing to the development of the robotic software and kind of like this whole industry flourished because of that thing because of ROS. Um, so so the question some might ask is like, okay, it's all great. So where can you install ROS? Like where is ROS being installed? So there are like a lot of different places. Like any robot that you can think of, there is generally some kind of a ROS implementation that was tried on that robot. So this page basically lists all the robots that ROS is installed on, and this is basically from the ROS website. So like if the robot isn't if the robot has ROS implemented and then they just go to the website and say that okay, we implemented on this robot. So there is a lot more robots that have ROS which is not even on this list. So as you can see, it is on the ground, on water, on air. It is also in warehouses, in factories, in outside in fields, in research labs, so everywhere that you can think of. Um, I mean, again, this is obvious now. 10 years ago, this was a dream, like for a robotics software framework to have been implemented and being ubiquitous everywhere. That was a dream, and now it's kind of like a reality. So it's kind of a big deal. Okay, so let's take a step back and see what was before Ross came into the picture, right? So this was like 10, 15 years ago, right? If you're developing like if you're developing robotic software, this is kind of the workflow that you would go through. So you will look at a paper and you will see, oh, that is a great idea. We should do something like that. I mean, I can build on that. So then you're kind of try to see, okay, how can I use it? So it's probably some repository. And you want to just make the software work, and you look at the software and you spend a lot of time, um, and you kind of figure out like, okay, that software is a mess. I don't understand what's going on. It's going to be really painful for me to get to deal with it. So what you do is you say, okay, let me come up with a plan and let me rewrite the whole thing. Like let's create a software API that we can use. Um, and then you spend hours and hours trying to set it up. So I've been through actually this setup. I have set up like a couple of software frameworks that we could use. Again, this is like 10, 15 years ago. Um, Basically because there was like the software that we got was crap and we didn't know how to properly integrate it, and we said, okay, let's just use it. But what eventually happens is we all of us humans do underestimate the complexity or the amount of effort it takes to untangle things. So we basically run out of time, and we think, okay, so now we just have to do things that we can do. And this is particularly the graduate student case where they have to just publish something. So what they come up with is they would just go ahead and just implements stuff that they can barely demonstrate that they think works. Once that happens, they just publish it and then they're done. Um, but the cycle repeats, right? So you have published this thing that is again crappy. Someone else picks up, and the whole cycle repeats over and over again. So this is what is basically a problem in robotics that was happening for like several decades. And now with ROS, actually this solves it, right? Because now you have this thing, you publish it as in a package, and then someone else comes in and uses it. So if you think of it, it causes an exponential growth because now you're not redoing the same thing over and over again. So every new effort that comes in, it translates into actual real progress in the field. So this is what has helped Ross to take the robotic software into a whole new trajectory. So a bit of the background. So origins, like ROS was invented in the like founded in 2007 by Willow Garage, and their initial goal was to standardize the robot software, create reusable components, and build collaborative ecosystem, which I think they did accomplish those goals. And then these are other key milestones like ROS development began in 2007. In 2010, the first official release happened. In 2012, Willow Garage, it was kind of like a startup, and Robotics Foundation actually took over the work from Willow Garage. Um, so just to look at the that same time frame, there were a lot of different frameworks available at the time. Like ROS was not the only kind of framework that claimed to do what it did. So there was this play stage thing that integrated closely with Gazebo, having this plug and play kind of an architecture. There was also this URBI platform that allowed a similar kind of an architecture to ROS, where you have these different components that you can plug and play. And then there is also this YARP, the yet another robot platform. So there was a lot of these different platforms, but all of these kind of lacked something, right? Like they probably didn't have the tooling that was needed. They didn't have the plumbing that was needed or the infrastructure that was needed. And Ross did have all of that, and basically um, progressed further. So what it's kind of obvious from if you look at the metrics, right? So if you look at the number of ROS users over the years, it kind of like skyrocketed. In 2009 and 10 time frame, it was kind of nearly nothing, but then as years went by, it just kept growing. So another metric you would definitely look at is the number of repositories. So even early on, like the repositories were kind of like there was a lot of repositories, and now it still keeps growing. So this basically shows that ROS is not at its peak. It's still a growing platform because nothing has slowed down or flattened out. So even now, if you learn ROS, it's going to be useful for you because it's going to stay kind of current for the next couple of years, maybe even decades. So the next part is um, like the different like the different distributions. So ROS is basically distribution based. So there's been like 13 major distributions in ROS one. So let's look at them. So the first one, as I said, was the Box Turtle release. So that was done in 2010. The second one was Sea Turtle. It was kind of an incremental update. The third release was Diamondback. It was in 2011, the next year. So this one was kind of like an interesting release because if you I don't know if you guys know or remember, the Kinect sensor was introduced. So this was like an Xbox based sensor that can detect your whole body, and it can use that and to control an avatar on your game. So the robotic community kind of soon figured out a way to use that, and then it produced really clean point clouds for a much cheaper kind of sensor data. So if you're looking at a point cloud, a sensor that can produce really clean point cloud as Kinect sensor, around the time you would have spent at least like $5,000 to $10,000 to get that, and the Kinect sensor was just like a $150 kind of sensor. So that was a huge explosion in point cloud data, and so ROS integrated the Kinect sensor drivers and then the infrastructure around that time. And then there was also this point cloud library that was the PCL that came into play. There were different point cloud libraries around that time, but this one was really kind of integrated all the state-of-the-art algorithms, and also provided a more flexible and efficient way of putting together these point clouds together. So this was a big deal, and and then this was the kind of a big distribution. As you can see, like all of them have some turtle picture, so that's kind of what that's a kind of a Ross thing. It's all some kind of a turtle that they use. It's kind of like a mascot. And then came Electric in 2011, where they expanded the support for other architectures like ARM or Android and Arduino. 2012, they had these Fute, and that's when the Catkin build system was introduced. ROS is primarily using the CMake build system, but then Catkin build system allows you to uh, build these different frameworks, like cross compile for different frameworks or architectures from the same system. So this was really important if you're trying to build systems that can be deployed in different architectures. ROS kind of incorporated that and added that functionality. In 2012, there was Groovy, and in 2013, there was Hydro, which kind of improved the Gazebo integration. So Gazebo is the simulator in ROS. Gazebo existed even before ROS was kind of formulated, but this kind of integrated Gazebo much closely into ROS, which made it a lot more kind of like ingrained or much more integrated server or much more integrated simulation for ROS infrastructure. So, and then Catkin was made a default in this distribution. So the next part was like Indigo. Like this was the in 2014, and it's an LTS release, which is a long-term support release. So what this means is long-term support is basically where you have a release that can span for like they will have support for 5 years, and this is something that um, Ubuntu started doing, I think in around like 2008 or 9 timeframe. So this allows stability, so that if you're a company setting it up, you need this kind of stability and support, so that you know that this is going to be supported for the set number of years. So that's what happens. And Indigo is the first LTS release. It's also the most popular release. And then came Jade, and then Kinect. Kinetic. So this one, the Kinetic was kind of like a also an LTS release, um, and another really popular release. Like um, I still remember like there was a lot of robots. At this point, ROS was really mature, and this was kind of the go-to environment. So any robot we kind of like mint at this time, it will have the Kinetic framework on it. And then came Lunar and Melodic. So Melodic, this is like Ubuntu 18.04. This release, we still have some robots still running Melodic. Like one of the Lunar robots that we have is still running Melodic in it because of the hardware and software dependencies we have. And then came Neotic in 2020, and this was a final release for ROS1. And it's kind of like its end of life release, end of life support is 2025 this year. So going beyond, like going into 2026, there is no ROS1 thing that is a release that is supported at this point. So it's an important thing to note. If you're developing software, you have to start with ROS2. You should not be like, it's not recommended to start any software in ROS1 at this point. So that's kind of like the major part about ROS1. So I think the next part is ROS2. I'll stop here. I guess Sumant and um, the other person has dropped by.
Jishnu.
Krishna. Yeah, Jishnu also dropped off. I don't know if they have connection issues. We're also at the top of the hour, so maybe I'll just pass here. Krishna, do you have any questions?
Uh, right now, yeah, I don't have any questions.
Okay, cool. So how's it going? I'll pause the presentation here. We'll pick it up next week.
Yes,
So I guess Sumant is joining.
Jishnu said he has network trouble.
Oh,
So
I see. Okay. Okay. That's fine. So anyway, I mean, we'll have the recording too, right? So we can listen to it. So I'll stop the stop here, and we'll pick it up, like talk about ROS 2 next week. Um,
sure.
so I guess, like, if you have any questions related to this one, and or maybe even general questions, let me know. I think we have like 12 more minutes.
Uh, Sir, like right now, I have a problem with like, what do you think about Ross with ChatGPT? Like, it is solving a lot of it. So I'm kind of having an existential crisis kind of thing for it because of
Yeah, okay. I'll talk about well, I have like I don't know, you joined a little late, right? So I do have a lecture on AI tools. So I'll talk about
yes, sir.
that. But to answer your
Sure, sir.
question, the you can think of this as like the 80/20 rule. So with AI tools, um, they are going to do 80% of the work. That's pretty much close to 80% of the work. There is no denying that. But there is this remaining 20% that still needs to be done by humans. So that is the area you need to focus on. So if you say, if people say that, oh yeah, robotics, I mean AI is going to kind of completely replace humans, maybe it will, but not anytime soon. So just think of it as okay, there is this remaining 20%, and what are the things I can do? What are the things I can um, make sure that that remaining 20% is really rock solid, and and we can make it work. So when I say remaining 20%, I'm not referring to, oh, the robot, right? I mean, the AI tools write 80% of the code and you write 20% of the code. No, I'm not referring to that. The AI would probably write all of the code, but your job might be to just go in and see, like, if the code makes sense, review the code, and point out issues, things like that, right? Like, for any software development, it's not just writing code. It is like writing the code, basically like starting with the design, doing this high level design, and then jotting down these different components, figuring out how these components interact with each other, and then writing the code for these components, and then testing if these components do their task individually, like the unit testing, and then do some kind of integration testing, see how this interaction between these components happen, and then going on and doing this system testing where you put together the whole thing and make it all work. So A is kind of like catching up on all these areas, but it's still not doing this whole thing, end-to-end thing, properly. So and then I also left out some early parts where requirements, right? How do you get the requirements? How do you make sure the requirements is kind of like accurate to what is needed, and those kind of steps. So when you start to think about it, there is a whole bunch of things that needs to happen, and AI is just taking parts of it. So your job is to make sure that you kind of like fill in the gaps, make sure that Ross does things the right way, or sorry, the AI does things the right way, and that's kind of like the major deal. So the way you should start thinking about yourself is not like a programmer or a developer. That kind of role is slowly going away. You should start thinking about yourself as a team lead, or a manager. That's how it is going to be going forward. So another analogy I can give you is, um, a couple of decades ago, people, when computers were new, people were programming in assembly language. You know assembly? Like, heard about it?
Yes, sir.
Right.
Basic
So,
language, right? Mm.
well, not well, basic is itself a language. What I'm referring to is like the assembly languages, the language that you would like, things like, okay, moving data to a registry, and it's basically like what the microcontroller or a microprocessor basically understands, instructions for those low level architecture. So the high level components like the C++ program, or a C program, or a Python program, these are basically high level languages that convert the code into some kind of machine language, which is doing these assembly kind of instructions, right? So a couple of decades ago, people were writing assembly code manually. They were doing all these things, and then compilers came in. Compilers basically took these high-level languages and molded into a way so that, or compiled them into binaries that the programs or the hardware can understand. So that kind of happened. So what really went on is, as time went on and the compilers become really great, people started looking into or writing code in assembly. Like, no longer do a lot of people look into or write assembly language. Like, most people don't even know what assembly language is. If they haven't programmed 20 years ago, they probably don't know what it is. So that's kind of like transformation that AI would bring, where maybe you will not have to look at a C or a Python program anymore. Um, and all you have to do is make sure that it does the high level bit, like how we just write Python program now, but don't look at the assembly language because we trust the compiler so much. So that's the kind of stage we'll get to. I still think that might be like a couple of years away, maybe a decade. Um, but but that's that, right? Like, even when that happens, there'll still be more things to do for humans. So um, for your question about existential crisis, what I would say is, like, history has kind of repeats itself, right? It has gone through these phases over and over again, and every time what happens is people feel that, oh my God, this computer or this machine, like when the industrial revolution happened, is going to take over my job. I'll not have any job. What we have seen over and over again is, like, we end up having more tasks to do and needing more people to do those tasks compared to the number of things that these automations can do. Um, so I believe that history will repeat itself again here. What we have seen is, like, when these automations become better and better, the level of job or the kind of things that we do actually gets better and better. So in the past, during the industrial revolution, people had to work in factories uh, around the clock and burn themselves. But now it's not the case, because a lot of people have white collar jobs, right? You just sit in your computer, you can work from the comfort of your home. Um, so yeah, I think our life would get better and better as technology progresses, and this is, I think, the way it would progress. Again, this is the optimistic way of looking at things. There's also a pessimistic way of looking at things, but we don't know what's going to happen. So why would you do look at the pessimistic way of things? Just look at the optimistic way and prepare yourself for that. Does
Then
this
how
answer your
would we
question?
learn? Like, like the basic part is, how should I learn? Like, should I learn from the basics, or like, uh, I'm not able to understand how to learn
Sure,
the
sure. Yeah, I can answer
ROS
that.
program.
Yeah. So I think what is really important at any point of time is having a deeper level of understanding. So that part never fails you. So what I mean by that is, like, uh, when you're looking at something, you can, let's say you're using a tool. It is good to know how to use a tool. Let's say a hammer, right? You're trying to use a hammer, and you can say, okay, by hitting a nail, that's all I can do. This is how I use a hammer. That's great. That's one level of knowledge, knowing how to use a tool. Now you can go deeper. You can say, like, okay, how else can I use a hammer? I can use hammer to break things, but I can also use hammer to build things. So maybe there is a different way of using the hammer. So now you develop some deeper understanding. You can go even deeper. You can say that, oh, how does an hammer even work? So basically, it means that when I have some force, I'm kind of like concentrating that force into a particular point, and then when I hit it, it kind of have this focused effort and can even drive nails into wood. So where can I use this knowledge? Can I use this knowledge to build something? Maybe you can develop a hammer drill, because now you know how a hammer works. So you can, if you think about it, like, for anything you can go even deeper, right? Like, there is always this deeper level you can go. So having going into this deeper level definitely helps in both your understanding, but also in your in future proofing yourself. So not everyone will have the appetite for going deeper, but how much ever deeper you want to go, and maybe go one more level deeper, because your brain is set up so that it doesn't want to strain or do things that you're not familiar with. But if you kind of like force yourself to go like one more level deeper, you would kind of like get to the cutting edge. So all that matters is you have this world where you have a lot of people, but if you're in the top 1%, if you're in the top 10%, then you don't have to worry about your existential crisis, right? Because you'll always have something to do. Because if you're on like the top 1 or 10%, then there's always a need for you somewhere, and people, you will find some job or some business that you can work on. So the way to get to that top percentage is having this curiosity to go one more level deeper. Does that kind of like address what you're asking?
Sure. Yes.
Okay. So there is no magic bullet. So that's another thing that I want to tell here, right? Like there is nothing like, oh, do this or do that. But one thing that I can say that's a meta thing is be curious. If you don't know something, just try to dig in and see what it is. So if I say like just go a little deeper, um, trying to do that without having this notion, like without having curiosity, is really hard. That will be like painful. But if you're having the curiosity, we are like, okay, why is it working this way? Like, what makes it work this way? Then you actually have the get this thing where you will be pushed to actually look into it, and it will not be a chore anymore, and it'll be uh, just out of curiosity you wanted to learn that. And that's how I've been learning. I'm not like a superstar kind of performer or anything like that, but my only superpower is like I am curious. I'm curious about everything. So I just dig in. And that's how I kind of learned about a lot of things. So that's what I prescribe to you guys too.
Yes, sir. Thank you.
Thank
Sure.
you. Yeah.
Okay, cool. I guess we're at the top of the hour. So I'll end the session now. I'll talk to you guys next week then. We'll continue with Ross too.
Okay. Thanks for your time, Srini.
Yes.
Bye.
Sure, no
Yeah.
problem. Okay,
Bye.
see you guys. Bye.